When you bring up the topic of who created calculus, you could come across two different answers. Some would tell you that Sir Isaac Newton was the one to come up with the idea, and they're right. But others would tell you that Gottfried Leibniz was the one to do so, and again they are right. You see, although they did not work together and had very little if any communication between them, they both managed to stumble upon the beginning stages of calculus. Sir Isaac Newton was a jack of all trades when it came to science and math. He spent his life developing new methods and theories in almost any field ranging from astronomy to mathematics. The first problem that Newton tried to face was the slope of the curve. It was possible to find the average slope of a curve, but depending on the point you were looking at, the slope was always changing. He came up with the idea of differentiation and how it approximates the slope of a curve as the interval approaches zero. This allowed him to create much more accurate assumptions of the slope. The difference between Isaac Newton and Gottfried Leibniz was that Leibniz was more willing to share his work with the public. Not only that, but he kept his notation neat and consistent, unlike Newton, who just used whatever he felt that day. However, since Newton had the more well-known name during their time, Newton was the one who received credit for calculus, and Leibniz was labeled a fake for plagiarism. An accusation that he never really overcame. Calculus is broken up into two main branches, differentiation and integration, which so happen to be opposites of each other. Differentiation is the part concerned with continuous change and its application. Differentiation is a very valuable tool that someone can have on their belt. It allows us to find the optimal point of a function, either that is the maximum or the minimum. It can also be used to find nearly an endless amount of information about a function and has many real-world applications, such as finding the correlations between sales and cost to maximize profits. It could be used to find the most efficient method and number of people needed to run a certain task, and could be used to determine the velocity and acceleration of any given number of objects or machines. The other side of calculus is integration, which is the process that, in the most basic terms, is the reverse of differentiation. This allows us to add infinitely many infinitely smaller numbers. This could allow us to find the area of any geometric shape or the volume of a geometric solid. And just like differentiation, the uses are nearly endless. Calculus is the basis to physics, engineering, and many other higher math courses. It is also very useful in chemistry, astronomy, economics, and statistics. What is engineering? Engineering is the application of science and math to solve problems. Engineers figure out how things work and find practical uses for scientific discoveries. Many times scientists and inventors get the credit for innovations that advance the human condition, but it is engineers who are instrumental in making those innovations open to the world. Physicist Freeman Dyson wrote, "A good scientist is a person with original idea. A good engineer is a person who makes a design that works with as few original ideas as possible." There are no prima donnas in engineering. The history of engineering can be taken back to the time of the pyramids, Stonehenge, the Parthenon, and the Eiffel Tower. Today's engineers not only build things on a massive scale, such as the International Space Station, but also on a much smaller scale like microchips. What do engineers do? Engineers design, evaluate, develop, test, modify, install, inspect and maintain a wide variety of products and systems. They also work out which type of material or with method of production will work best for a given product. They are usually broken up into four main areas, but also hugely overlap into each other. Mechanical entails the design, manufacturing, inspection, and maintenance of machinery, equipment and components. Electrical is the design, testing, manufacturing, construction, control, monitoring, and inspection of electrical systems. Civil involves the design, construction, maintenance, and inspection of large infrastructure projects. Chemical is the practice of designing equipment, systems, and processes for refining raw materials and for mixing, compounding and processing chemicals to make valuable products. An example of calculus in engineering. Suspension bridges. The concept behind this example is parabolas, the basic definition of which is a conic section formed by the intersection of a cone and a plane. Suspension bridges are the most commonly built bridges. They are known for their long spans with high vertical supports. In between these supports hangs these long cables. The suspension cables hang over the towers until they are anchored onto land towards the end of the bridges. The way in which these cables hang form a parabola. Suspension bridges are able to go long distances and hold up a large amount of weight due to how the cables are put into place. With the weight of the actual bridge and the weight of all things on top of it, it creates two types of forces acting on the bridge: compression and tension. The parabolic shape of the wires is what allows the bridge to address each type of force. The deck of the bridge sags from all of the weight of the traffic because of compression forces, which travels up the cables. They then transfer those compression forces downwards to the vertical towers, into the foundation. The cables receive the brunt of the tension forces, as they are supporting the bridge's weight and its load of traffic. But why is the parabola the optimum shape for the cables? First, you have to know the three forces acting on the cable: tension, weight, and the force tangent to the cable at a point, we will call force X. We know that the slope of force X is the same as the slope of the cable, which is what we need to find to get the best shape of the cable. So the slope of force X is equal to the weight divided by tension. But what is the weight? We know the weight is distributed evenly through the deck, so that means it also has a uniform density, we will call density U. So we now know that the weight is equal to the density times the distance from the origin to the point of force X. With all that information, the slope of force X can be written as force X is equal to density U times distance X divided by tension, which is the same formula for the slope of the cables. Now if we take the integration of that, it will give us our equation for the optimal shape of the cables. Let's look more in a broad sense about how calculus is used in mechanical engineering. As an engineer, you should be able to use various forms of differentiation, such as partial differentiation, separation of variables, rate of change, and Fourier series to find things such as fluid flow, heat transfer, combustion, and computational solid mechanics. For example, in automobile design, you can optimize the design of automobiles' internal combustion systems by modeling pressures in inlet valves, cylinders, and outlet valves. These calculations are used to model combustion efficiency and improve power outputs in vehicles. Now let's look at how integration can be used for electrical engineering. Integration by substitution, parts, partial fractions, and root mean squares can be used to design thyristor firing circuits, which are used in power supplies, photographic flashlights, dimming lights, alarm systems, robotics. Thyristors are solid-state semiconductor devices, similar to diodes, that act as switches. They are mainly used to control alternating currents where high voltages and currents are involved. Integration can be used to design thyristors for simple door alarm circuits and extremely complex robots.